we can confirm this thing with this graph geometrically from the graph of f, which is the elliptic paraboloid with the vertex 1 3 4, where x is equal to 1, y is equal to 3, and the value of the function is 4, which is at the center point as shown in the figure 1 3 4, where the value of the function is minimum, or we can confirm it directly from this graph. So in this way we can find the local minimum value of this function. Next, one important note for the values is that the fact that the function need not to have maximum or minimum value at a critical point, as I told you before, that if for the any critical point is not necessary that the at any critical point function have maximum or minimum value, right? So the main problem is we need to confirm that where at which critical point the function will take maximum value or minimum value, or neither. So these are we need to confirm this thing, that at which critical point the function makes maximum or minimum value, and for that we need to the following we need the following test to second derivative, known as a second derivative test for the function of two variable, which is very helpful to us to be able to determine whether or not a function has extreme value at a critical point. Okay, so using this test we will confirm that at this point, at this critical point, function has maximum, and at this critical point function has a minimum, or neither maximum or minimum. Okay, so let us look at the very useful second derivative test, and this method is very useful to solve the example where the function takes maximum, minimum, etc. So look at the statement of the theorem. Suppose that the second partial derivative of f, note that in the prior example we have only used the first partial derivatives, but in this test we will use the second partial derivative. So suppose that the second partial derivative of f are continuous on a disk with center AB. Second step is partial derivative of function with respect to x at the point AB, and partial derivative of function with respect to y at the point AB is equal to 0. That is, AB is a critical point. Note that this means AB is a critical point of function f. Then let D is equal to DAB defined by second derivative of function f, fxx at the point AB, fyy at the point AB, minus fxy at the point AB whole square. In this way define the second derivative DAB, f of xx at the point AB, fyy at the point AB, minus fxy at the point AB whole square. And we have some conditions using which we can say that at the point AB function will maximum or minimum, or neither maximum or nor minimum, etc. So in first condition, if D greater than 0, we can easily find the value of D using the second derivative of function at the point AB. And if D greater than 0 and fxx at the point AB both greater than 0, then FAB is the local minimum. Okay, function of value of the function at the point of B will be the minimum value, local minimum value of function. When in the second case, if D is greater than 0 is as the condition A, and fxs at the point AB less than 0, then function is at the point AB, function is a local maximum. So if we compare these two conditions A and B, in both D is greater than 0, but in first condition A, fxx at AB is greater than 0, and in the B, fxx at the point AB is less than 0. So in this way, if fxx at the point AB greater than 0, then the function is local minimum, and fxx at AB is less than 0, then the function will be local maximum at the point AB. The case number C is very important. If D is less than 0, note that if D is less than 0, then value of the function at the point AB is not a local minimum or local maximum. So before this test, we are not able to say that the function is maximum or minimum at which critical point. So from this test, we can sure that if D less than 0, then the value of the function at the point of B is neither maximum or minimum locally, right? This is very important test to find the local maximum and minimum values. So please note down this test, and you have to use this test in mostly example to determine, to get the local maximum and minimum. Note that in case C, we have already discussed that in case C, the value of the function at the point AB is neither maximum nor minimum. So this kind of point AB is called a saddle point. So now we are moving to the another small topic, which is saddle point. First, we have already learned about the critical point at which the function might be the maximum, minimum, or that point might be a saddle point. When at the point AB function neither maximum nor minimum, or we can say that D is less than 0. When D is less than 0, then the point AB is called the saddle point of F. And another important note is, if D is equal to 0, then what we can say, D greater than 0 and fxx is greater than 0. The first case, D greater than 0, fxx is less than 0. Second case, D less than 0 is the third case. And now the last case, when D is equal to 0, the test give no result. That means we cannot say that the function is maximum, local maximum, or local minimum, or a saddle point. So if we get the D is equal to 0, then this test will not be helpful for us to say that at the point AB function will be maximum or minimum or a saddle point. So just pray to God that D is not equal to 0 in our case, right? So this is the very important notice, that if D is equal to 0, we cannot find any result, any conclusion about the local maximum and minimum values, right? Okay. And how to remember this formula? Because this formula, as I told you, this is very important formula for the local maximum and minimum values. And to remember this formula for D, it is helpful to write it as a determinant. Okay, we all are very well aware about the 2 by 2 determinant. If we put in the first row the partial derivative of f with respect to xx, that means fxx and fxy, and the second row fyx or is equal to fxy and fyy, then the simple form of this determinant is fxx into fyy minus f at x fxy whole square, which is our second derivative test for the D. And if this D is greater than 0, then local minimum. If D is greater than 0 and fxx less than 0, then the local minimum, and D less than 0, then neither maximum nor minimum. And if D less than 0, then the point is called saddle points, right? So this is the very important way to remember this formula in the determinant form. So please note down this format to remember the second derivative test. Okay, now again we will look at the example, and the question is find the local maximum and minimum values and saddle points of the function of xy is equal to x raised to 4 plus y raised to 4 minus 4xy plus 1. So as first we will find the value of the function partial derivative with respect to x, which will equal to 4x cube minus 4y, and partial derivative with respect to y is equal to 4y cube minus 4x to find the critical points. And if we take fx is equal to 0, then 4x cube minus 4y is equal to 0, and if we take fy is equal to 0, then 4y cube minus 4x is equal to 0. Then by the calculating, we can get x cube minus y is equal to 0 and y cube minus x is equal to 0, and to find the critical point we need to solve these two equations, and to solve these equations we substitute y is equal to x cube from the first equation into the second equation. So we will get that x raised to 9 minus x is equal to 0, and by taking common x we will get x into x raised to 8 minus 1, which is equal to 0, and by simplifying it we will get x into x square minus 1 into x square plus 1 into x raised to 4 plus 1 is equal to 0. And so by solving this we will get the 3 real roots or 3 real values of x, which is equal to 0, 1 and minus 1. So we will get 3 critical points, as we know that x cube is equal to y. So we have here x is equal to 0, so y is equal to 0, x is equal to 1, so y is equal to 1, and x is equal to minus 1, so y is equal to minus 1. So here in this case we have 3 critical points, 0, 0, 1, 1, minus 1, minus 1, right? So we will use all these 3 points at the, and we will find whether the function is maximum or minimum, or any point is saddle point. Okay, so we calculate the second partial derivative and dxy. First, fxx is equal to 12x square is very clear, and fxy is equal to minus 4, and fyy is equal to 12y square using the question. Okay, so value of d is dxy is equal to fxx into fyy minus f of xy square, which we have already remember with the use of determinant. Okay, so fxx is equal to 12x square, fyy is equal to minus 4, and fxx is equal to 12x square, fyy is equal to 12y square, and fxy is equal to minus 4. So dxy is equal to 144x square y square minus 16. Now we will find the value of dxy at the point 0, 0, at the point 1, 1, and at the point minus 1, minus. First we will find the value of dxy at the point 0, 0. Then d0, 0 is equal to minus 16, which is less than 0. That means the case C, when the d is less than 0. Here d at the point 0, 0 is equal to minus 16. It follows from the case C of the second derivative test that the origin is a saddle point, not that the first critical point 0, 0 is a saddle point, as d is equal to minus 16 is less than 0. That is f has not local maximum or minimum value at the point 0, 0. Okay, so this is for the first critical point 0, 0. In the same way, for the second critical point 1, 1, if we take the value of d, then d is equal to 128, which is strictly greater than 0, and we have already known the value of fxx, and if we find the value of fxx at the point 1, 1, which is also equal to 2 and greater than 0, and this is the case number A. This is case A, in which we have discussed that if d is greater than 0 and fxx is greater than 0, then the function have a local minimum at the point 1, 1. So here d is 128 greater than 0, and fxx is equal to 12, which is greater than 0. So at the point 1, 1, function have a local minimum, and the local minimum value f of 1, 1 is equal to minus 1. Note that this value is local minimum is equal to minus 1. So first point 0